So hi, yeah, my name is Nick Spooner. I'm going to be talking about joint work with Alessandro Chiesa and Tom Gurr, who are also at Berkeley, and Michael Forbes, who is at UIUC. So let's start by kind of talking about what the words in the title mean. Firstly, zero knowledge. So hopefully a good number of you know what it means, but just in case. So suppose that I have a graph, and I want to know whether it's colorable or not, but all I have is my laptop. So maybe what I do is I ask some powerful server to tell me whether it's 3 colorable. And one way that the server can do that is I send him the graph and he says yes, right? But then, I'm not convinced in any way by this response. So maybe I say, okay, prove this to me. And one way he can prove it to me is by giving me a 3 coloring. Okay, but maybe now the server is not happy with this because maybe the 3 coloring was secret. It cost him a lot of money to compute it, and he doesn't want me to know what it is. So zero knowledge is essentially a way of saying I can convince you of something without giving you any additional information over the protocol where I just tell you yes. And in the classical setting, we know a lot about this. So this is in the classical single proof setting, we know a lot about this. So when we make a cryptographic assumption, we assume the existence of one-way functions, then we can obtain zero knowledge for all languages in NP or even P space. And this is a classical result. And it turns out that this is necessary, so you need to make cryptographic assumptions if you want to get zero knowledge for NP. Okay. So one thing that we can do if we're not happy with these cryptographic assumptions is modify the model slightly. So we are going to split the prover into 2 parts, and this is called the multi-prover interactive proofs model. And the idea is that the verifier can talk to both of the provers, but the provers can't talk to each other after the initial kind of setup of the game. And in the case, in the kind of classical case, we say that spatial isolation implies that the prover strategies are somehow local. And this allows us to obtain unconditional zero knowledge without any cryptographic assumptions for NEXP, which is the class of languages that can even be decided by this model. And so here, kind of unconditional zero knowledge is for free. This is the message. And this, we can write this as NEXP is contained in zero knowledge MIP. So this is from BGKW. I mean, they didn't actually know that MIP was equal to NEXP, but they showed this. In the quantum setting, things are different, because in the quantum setting, spatial isolation doesn't imply that the strategies are local. So the strategies that we can use now, they are kind of a broader class. So let me explain what I mean by the quantum setting. So Anand mentioned this earlier. So in the quantum setting, what we have is this model called MIP star, where the verifier is still classical and the communication is still classical, but now the provers are quantum, and so that means in particular they can share entanglement. So they prepare this state psi, and they split it into 2 parts at the beginning of the protocol, and then they can use it, measure it, operate on it during the protocol. So a natural question is, how powerful is this class? And it's not clear a priori, because in one sense the provers can do more, because the honest provers can do more because they have more power. They can maybe prove more languages, but on the other hand, the malicious provers can do more, and so that maybe they have more strategies with which they can fool me. So it turns out that the second thing doesn't happen, and in fact, NEXP is contained in MIP star. This is a result due to Ito and Vidic in 2012. But like Anand said, we have no known upper bound still. It might be the case that this class allows you to, this model allows you to prove undecidable languages. So a natural question to ask is whether this zero knowledge message also applies in the quantum setting, right? So like in the classical setting, the addition of a second prover allowed us to get unconditional zero knowledge essentially for free. And the question is whether in the quantum setting this also applies. So is NEXP contained in ZK MIP star? So the answer to this question is yes. This is what we prove in the paper. And you might be wondering why this is difficult to show, because in the classical setting, the way that we can show it is we can say, oh, I can take any MIP protocol. I can apply some technique, some commitment scheme technique, and produce a zero-knowledge version of that protocol. So why can't I do this in the quantum setting? So since we know both of these things, why can't we kind of just put them together? And the problem is that there's kind of a mismatch of the way that these things work. So the only way that we know how to prove things are sound in the MIP star model is essentially algebraic. So we don't really know how to use these combinatorial techniques that are used to prove the BGKW results, how we can prove that these are sound in the quantum entangled setting. Whereas the techniques used in atomovitic, they're kind of inherently algebraic. And so how do we resolve this problem? What we do is we show that there are algebraic ways to obtain zero knowledge in the MIP setting, and these kind of lift to the MIP star setting in a natural way. Okay. So the proof is in 2 steps. The first step is a lifting lemma. So it takes some classical object, which is a special model of a PCP plus some interaction, and I'll explain what that is in a second, along with a lifting lemma that says if you have such a thing, then you can get a protocol that is sound in the entangled setting. And this lifting lemma, we show that it preserves zero knowledge. That is, if the thing you started with has a zero knowledge property, then the resulting protocol will have also a zero knowledge property. And then the main bulk of the work, so this first thing is actually just kind of adapting stuff that was already known. The main bulk of the work is showing that you can obtain zero knowledge in this model. And this model, the reason why it says algebraic ZK here is that this model is inherently algebraic. Okay. So, all right, let's start by looking at the lifting lemma. So this is stuff that is kind of due to Ito and Vidic and several papers after that, and we just kind of, I don't know, unpack it and make it into a lemma. So let's just start with the kind of basic case. Let's suppose that I have a PCP, right? In the PCP model, the verifier is allowed to make queries into this proof. And the lifting lemma essentially says that I can take this and I can do some stuff to it and produce an MIP star. It turns out the way that this happens is a little bit complicated, and in particular, this particular version of the lifting lemma doesn't preserve zero knowledge. So yeah, here everything is classical, I should say. Okay, so this is not going to be enough for us, A, because it doesn't preserve zero knowledge, and B, because it's not quite expressive enough. So it turns out that you can apply the same thing to this interactive PCP model. This is due to Carl Raz in 2008. So you can apply the lifting lemma equally well to an interactive PCP as you can to a standard PCP. So we will need that. And then we'll need to restrict ourselves slightly because, like I said, this doesn't necessarily guarantee that we preserve zero knowledge. And what we need is this thing called a low-degree interactive PCP. So a low-degree interactive PCP is a PCP where we're restricted to sending an oracle which is a low-degree function. So this means that it's some multivariate polynomial and it has bounded degree. And once we have that, once we know that our underlying object is a low-degree interactive PCP, then we can lift directly to something that is, to a multi-prover protocol that is secure against entangled strategies while preserving zero knowledge. So this transformation preserves zero knowledge. All right. So let's take a look at how the lifting lemma works. So as with most of these things, you have kind of this, you flip a coin with probability half, you do a low degree test, and probability half, you run your protocol. So the low degree test, let me just explain what it does. So you can think of both of the provers as having some low degree functions in their heads. And you ask one of them for a point, and you ask one of them for a plane. This is pretty much the classical low degree test. And what your low degree test guarantees is that all the provers are doing with their entanglement of all the possible strategies, what they are essentially doing is using it to choose some random low-degree polynomial and agree on it and then run the protocol. So the low degree test essentially amounts to kind of restricting the prover's behavior to be something like this. Then with probability half, you are going to emulate this interactive PCP that you constructed. So the first thing we do is we do a query reduction. You can show that this can be done without loss of generality and also without loss of zero knowledge. And then you kind of take this interactive PCP and you kind of break it up into two parts. So kind of one of the provers is going to be the interaction part, and the other prover is going to take care of the query. And what you note is that in the case of the prover that's taking care of the query we can show is uniformly random, and this means that he can't tell which world he's in, whether he's in the world where the other prover is being asked about the interactive PCP, or whether the other prover is being asked about the low degree test. And this means that his strategy in both cases has to be the same, and in particular, this means that he's thinking of a low degree polynomial and he's not doing anything funny with his entanglement. Okay, so in the last however many minutes I have, I'm going to talk about algebraic zero knowledge. And so this is kind of the main focus of this paper. So one thing that is very important in all zero knowledge constructions is commitment schemes. And we're going to need a kind of an algebraic type of commitment scheme. So we want to be able to commit to polynomials. And so what is a polynomial commitment scheme? Well, we can imagine the prover thinking of some polynomial q, which is over a finite field. And he commits in some way. And then there will be a decommit phase later on where the verifier can ask a bunch of queries. So he can say, oh, I want q of x, I want q of y, etc. And the prover has to respond with some field elements that correspond to these evaluations. So we want two properties. Firstly, if you don't ask me about y, then you don't learn q of y. Okay, so this is kind of the hiding property of this commitment scheme. And the other property is that you want the commit phase to uniquely determine q. So this is kind of I haven't specified what the model is going to be yet, but this is kind of the general idea of what a polynomial commitment scheme will look like. So let's think about how we can build one of these things in our low degree interactive PCP model. What we're going to do is we're going to look at the simplest possible case, which is when m is 0, so there's just one field element that I'm trying to hide. And I want you to kind of not know anything about it unless I tell you. So you commit to this message beta, which is a field element, and the way that you do it is you send a random polynomial, which sums over some chosen product set to beta. So here we have this h to the m set, and this is contained inside my finite field somehow. And I send you this polynomial, and it sums to beta, which means that when I've sent the polynomial, the value of beta is fixed. It's just this whatever this set of evaluations sums to. So this kind of already seems to fit what we mean by binding. And then when you decommit, okay, I need to be able to decommit in a way that is sound. And what you do is you decommit interactively via the sum check protocol, right? So we have a low degree polynomial that we're trying to check a sum. How do we check the sum? We check it via the sum check protocol. So this amounts to a decommitment. Right, yeah, so this is a very classical protocol for showing exactly what we wanted to show. Okay, so that's binding. How do we show hiding? Well, given an oracle, which is just without any low degree stuff, just a standard oracle, it's clear that this scheme would be hiding, right? Because if I set h to be 2 and m to be kind of linear, then I end up with something that's exponentially large, and I can't possibly make that many queries in order to learn the sum over this hypercube. So computing this value, this summation takes h to the m queries to my oracle. But what I actually have, and what I need, because I need the sum check protocol to be sound, what I have is a low degree extension of this, right? So I have some polynomial which matches this guy on all of the points in h to the m. And the question is, does this make this value easy to compute now, right? Is this value still hard to compute? And this actually is this is a question about algebraic query complexity, which is something that was introduced by Aronson and Vigdisson in their paper on algebraization. And it turns out that the answer is no. And the reason is, so the answer is no for this particular case. So in the case where we take the lowest degree possible extension, and we look at the kind of 0, 1, you can also do it for other subsets, but if you take the lowest degree possible extension, then it turns out that this is, you can learn the value in one query. So you query the low degree extension at this point, like 2 to the minus 1, 2 to the minus 1, and this gives you a scaled version of the sum. So what has happened here is that this encoding has kind of leaked information that I didn't want you to know. Okay, so this is a problem, but it turns out that you can fix it. So if your degree is slightly higher, so in the case of when h is of size 2, if your degree is at least 2, if you take that just a multi-quadratic extension, a random multi-quadratic extension, then finding this computing this summation still takes something like h to the m queries. So that is good. This means that now this commitment scheme is hiding. Okay, so I guess I probably have a little bit of time, so I'm gonna look at just how you commit to a polynomial using this scheme. 3 minutes, cool. All right, so I didn't expect to have so much time, so I'm gonna give you some bonus slides. So far we've been able to commit to just a single fill element, which is not super useful in terms of polynomial commitments. So how do we commit to a whole polynomial? And the way that you do it is actually quite simple. So what I do is I take a polynomial with many more variables. So it has 2m variables rather than m. And I say that the polynomial that's committed to that's committed to by this polynomial, so I have a polynomial p and it's committing to a polynomial q, and the polynomial q is just given by summing out some of the variables, right? So it looks kind of like this. This is p. This is kind of the floor, and q is given by summing out some of the variables over h to the m, right? So these triangles represent summing. And so what this means is that now I have a way to kind of represent a polynomial q using a bigger polynomial p, such that now I can decommit to anything in q. And I can decommit to any evaluation using the sum check protocol again, right? Because I can just say, oh, I look at the restriction of p to where I set the first m variables to be beta, and this is q of beta, and then I can just decommit to q of beta via the sum check protocol. There are a couple of problems with this. So firstly, you could leak information about linear combinations of entries in q, and this would still be bad because I don't want you to learn anything about q besides the things that I tell you. And also the decommitment of this q of beta could leak information about other things. So by doing the decommitment, I could, in addition, leak things that I don't want you to know about. But it turns out that this doesn't happen. So we can show that neither of these things occur. All right, and so I'm going to finish by going back to my open questions. So firstly, one of the big open questions that we have for this topic is whether some BGKW type result also holds for the entangled setting, for the quantum setting. So is it the case that MIP star is equal to ZK MIP star? So if we were able to resolve the problem of MIP star being, if MIP star is equal to next, then we already have this. But if that remains unresolved or it's bigger, then it would be nice to show something like this. This would give you kind of a more general thing. Is it possible, this is kind of related, is it possible to lift other protocols? So this IPCP model is limited to NEXP, so in the case that MIP star is bigger than NEXP, then we'd want to have some other way to do lifting. We want to be able to lift things that are kind of more powerful than the IPCP model. And finally, so everything here is like focused on testing kind of the read-Muller code. And so a good question is whether the read-Muller code is necessary or whether it turns out that you can use kind of any tensor code to obtain entanglement-resistant things, in particular tensor codes that maybe have better parameters than read-Muller. Okay, thank you very much. No. It's an interesting question, though.